All right, welcome back, Hack the Hollow. So this week's engineering challenge is actually going to be to prototype a model of something that I'm using currently in my Mars farm to keep track of the amount of water in my plants. I'm currently using 3 sensors, however, you're only going to prototype 1. What I am using is an analog moisture sensor, which sends its value to the Arduino. It's mapped out to be a real-world percentage of how well the soil is watered, and it conditionally lights one of 3 LEDs depending on the parameters that I have set. If all are above 75% watered, we should have a green light. If we are below 75%, we're going to get a yellow light. And once we cross the 50% threshold, we are going to get a red light. So you're not going to have access to the moisture sensor. You'll be using a potentiometer. And then you'll also be wiring a momentary push button to help calibrate the sensor in order to understand what the watered value is once you've added it to your plants. These moisture sensors have a similar wiring scheme to the potentiometer. There is a power, a ground, and an analog wire which reads the value from the sensor. Our push buttons are going to be wired such that we use the input pull-up resistors built into the Arduino. This specific circuit is using an I2C LCD, which only needs 4 wires for connection. The ones that you'll be prototyping on Tinkercad has 16. So this particular tower traffic light requires a 12-volt power supply because the Arduino can only supply 5 volts. Now, in order to turn that power supply on and off when we need to, we are making use of 4 separate transistors. However, switching a transistor on and off requires the same exact logic line as turning an LED on directly with a digital write from one of the digital pins. If you're in this challenge, that means you've just earned your creator badge and are ready to put together some of the skills you've been earning over the first month of our courses from home. So what we have today is a water monitoring prototype that we're going to use to sort of simulate the system that I showed you in my Mars farm here at home. So we're going to introduce to you a new component today, the LCD, so that we can get some field use out of getting data that we can see as opposed to having to look into the serial monitor to see the value of our sensors, which can be really useful when you're actually trying to implement one of your projects. So I'm going to walk you through right now simply wiring that LCD screen. The potentiometer, the button, and the LEDs you should be familiar with at this point. Now you can take a look and pause this video multiple times as I go through it to see how I've wired some of those other components, but for this purpose I'm only going to go over the LCD. So in this version of an LCD, you're going to see that there's quite a number of wires that it takes to get going, which can be cumbersome when you're working with something like an Arduino Uno because it really does eat up a lot of your digital pins. I like to use one that's known as an I2C LCD, in which I only use 4 total wires. But we don't have that as part of most of our kits, nor do we have it in Tinkercad, so we'll make use of the kit that we have. So right now we're going to walk across, and we're going to go over all of the pins that are necessary in order to hook this up. So starting furthest to the left, the first pin is going to go to the ground rail. The second pin to the power rail. The third pin is going to go over to the wiper of a potentiometer. Now in real life, that potentiometer is used to adjust the contrast of the LCD itself. Within the Tinkercad simulation, it doesn't do a terrible amount, but I thought it would be good for you to see a complete setup. The I2C backpacks that I use for the LCDs also have a built-in potentiometer, so they tend to not need one, which is another great feature of them. Back over to the pins. Starting with the 4th pin, you'll see that there's a blue wire going over to pin number 12. The next wire, number 5, is going to go to ground. And the 6th wire, which is a purple one, heads on over to number 11. We're going to leave number 7, 8, 9, and 10 blank. Okay, there's no connection for those pins. Starting with pin number 11, the pink wire goes over to pin number 5. The brown wire on 12 goes over to 4. The gray wire on 13 goes over to 3. And the yellow wire on 14 goes over to 2. That leaves us with 2 pins left. Number 15, using a 220 ohm resistor, gets hooked up to power. And number 16 goes to ground, and that's going to hook up the internal LED so that we can light this guy. So there you have it. That's how you wire a 16 by 2 LCD. Now it's worth mentioning right now what that 16 by 2 means. There are 16 columns and 2 rows on this LCD. And we use the same numbering convention that I taught you about when we talked about arrays. So the very first column is column number 0, and the last column would be column number 15 for a total of 16. And as far as the rows go, the first row is row 0, and the second row is row number 1. So don't forget your counting convention when we're coding and using electronics. In looking at today's code, you're going to notice a couple of things. Number 1, I use a lot of comments. That's to help you visually keep up with what I'm saying to you. You're going to want to pause frequently during this recording in order to get yourself caught up with what I'm describing. Next, you're going to see that there's a lot of incomplete code today because I believe that there's a lot of skill you've picked up over our first month together, and I'm going to challenge you to use what you've learned here. Now the first part is going to be a bit new to us, so I've given you all the code that you need. This is the first time you're seeing that we're using something called a library. Libraries are really useful in code because you can take the hard work of talented programmers and integrate it into your own work. Now to call a library, we often use a preprocessor code called a hashtag include call, and then we put the name of that library's header file in brackets or quotes. Now, as far as the simulator on Tinkercad goes, all you have to do is go to this file folder icon, and you'll see that there are a number of libraries that you can call directly into your code. And that's all I did up here at the top. Next, we're going to create a bunch of variables that are going to hold the values of all of the pins that we connected the LCD to using all the wires from the wiring diagram. We're not really going to go into reasons why we're using all of them because it doesn't really matter for our purposes today, but it cleans up the ability to call the object, which is what's going to start on line number 8. If you think of this example, it'll probably make more sense as to what an object actually is. Imagine I go to my library and I take out a book about dog tricks, and I learn commands such as roll over, sit, and speak. Now those commands are great, but I still need a dog to use them on. So if I go home and talk to my golden retriever, Penny, Penny would be the object on which I'm going to use that library. So before I can say roll over, I would have to say Penny, roll over, or Penny, sit. The equivalent of that in our code starts on line number 8, where we call the name of the library Liquid Crystal, because LCD stands for Liquid Crystal Display. And then we give our object a name. Now, typical to variables, you can name this anything you want, but it is the convention to name it something that makes sense, and I'm going to keep it simple and simply call it LCD. Now, calling this object does require some parameters. This library does need to know where you plugged in all of those wires, and that's what we stored on line 5 in all of the variables that we created. And again, don't sweat it so much this time around. I'm simply giving you the values that you need. Next, let's take care of our button and our potentiometer. We're going to create a few simple variables to store their locations. You'll see a byte variable on line 11 called sensor pin, and that's going to be in A0. And on line 14, you're going to see a byte variable called set button pin, where I've plugged it into pin number 7. Now recall a little bit about buttons that we learned from our previous lessons. We are going to need to debounce them, so you'll see that I've included the same variables from our previous code here on lines 15 through 17 to accomplish that task. Now it's worth noting a little something about our potentiometer today. The potentiometer is nothing more than an analog input, as is the moisture sensor you saw at the beginning of this video. We don't have moisture sensors available to us in Tinkercad, however the potentiometer is going to serve the purpose in our prototype today by giving us an analog input, and the algorithm that we write together is still going to be able to be usable the moment you get your hands on a real-life moisture sensor. On line 20, you'll see our first incomplete line of code. I've started by declaring a byte variable, but what you are going to do is declare an array called LED pins to hold the values of our green, yellow, and red LEDs, which I've plugged into pins 8, 9, and 10 respectively. I've also included a count variable for those LED pins to use later on in a for loop on line number 21. Typically when you use something like a moisture sensor, you're going to need to do something called a two-point calibration, which means understanding the bottommost value that it's going to output and the topmost value that it's going to output depending on what it is you're measuring. Now for our purposes, we're going to set those arbitrarily using our potentiometer. So when the soil is dry, we are going to say that it's going to give us a reading of 900. Now we have to keep something in mind with our moisture sensor. The higher the reading of the moisture sensor, the drier the soil is going to be. So we're going to start off by calling our soil watered value as being 0. Now this is definitely not what the sensor is going to be looking for because it typically is somewhere in the 2 to 300 range. But let's keep this in mind as well. Not every container is the same size and not every plant is going to require the same amount of water. So what we are going to do is have this value set when we hit our set button later on in our code. As you know by now, the void setup location is where we're going to initialize all of our hardware. So on line 31, I'm going to initialize my serial communication for debugging. On line 34, I'm going to initialize my LCD object by using the begin method. And the parameters 16, 2 are values for our LCD that are going to give me the number of columns and the number of rows. LCD.print is the way that you are going to write to your LCD, and it holds a very similar format to when writing to the serial monitor. So you'll see here that I've done nothing more than write the string plant condition in quotation marks. On line 38, I want you to initialize your set button using the input pull-up pin mode. And on line 41, I want you to use a for loop to declare each of your LEDs as outputs. We're going to start simple in our void loop by simply polling our sensor. So we are going to store the value in an integer variable, call it sensor reading, and I want you to complete the command for making an analog read of your sensor pin. After making a brief call to serial print on line 50 in order to debug our sensor, what I need you to do now is come up with the ability to read your button. Now, in order to do so, on line 56, you have to complete the line to make a digital read from your button pin. Next, on line 58, you're going to have to debounce that button so we don't get any false positives. Remember, in that if condition, you have to have 3 parameters that are met. The set button reading has to be low, the previous set button reading has to be high, and the amount of time held by the millis function has to have exceeded your debounce value that we set in the global variables section. Remember, they all have to be met, so you have to use an AND in between each of those parameters. Once they are met on lines 60 and 61, what you are going to see is that that soil watered value is going to be set to whatever the potentiometer is at that moment. So in this portion of the code, what I want you to do, before pressing your button once you simulate, you're going to roll your potentiometer to approximately 300, push your button, and what that will do is store the value of 300 as being your soil watered number, and that will finish your 2-point calibration. You'll then update the time on line 61, and you'll reset the previous set button reading value on line 64. Let's make a quick note about what exactly is going on lines 56 to 64. In addition to making your read from the button, debouncing it, and making sure that you can get a value that is stored in your soil watered variable that you declared in your global variable section, what we're looking to do is essentially calibrate our sensor. Keeping in mind that depending on the type of medium you're using, the size of the pot that it's stored in, and the plant that you're watering, the amount of water you add is going to be different from one plant to another. So essentially what would happen is you would put your moisture sensor into the soil, you would add your desired amount of water, you would then press your set button to store the value of the sensor that indicates a fully watered plant. Beginning on line 66, we're going to attempt to write some code that converts the sensor value into a real-world number that means something to the programmer and can be useful to the gardener using your circuit in their garden. So we're going to create an integer variable called %watered and make a call to the map function you learned about a few lessons ago. And what we will do is take the sensor reading and we are going to map it from the values of soil watered and soil dry, which have just been set after hitting your set value, and we're going to turn them into 0 to 100. Remember here now, 100 is set first because that's going to be equivalent to the lower sensor value. Our moisture sensor reads low numbers when there's a lot of water and high numbers when there's a little water. So now converting it from 0 to 100 essentially gives us a percentage we can use to gauge how much water we've added in our soil. Next, because our sensor isn't always super accurate at its limits, we're going to make a call to constrain. And we're going to ask that our percent watered never goes below 0 or above 100 for our purposes. And then we're going to print that to the serial monitor just in case we need to debug it. Beginning on line 71 is actually the fun part of our code where we can now create a conditional output based on the sensor input that we are getting from the real world. And this is essentially the essence of physical computing. So the way we are going to control the logic in this program is by using a grouped conditional known as an if, else set of statements. So essentially what will happen is the compiler will treat all three of these statements as one set of conditions, and it will look through each of these to make a decision as to which one should be used. Had we simply kept them as individual if statements, we could potentially have more than one of them hold true, and the logic will break down. So let's take a look at what we're doing here. On line 71, we'll begin with our if statement. And if you take a look at the parameters that have to be met, we just have to see that our percent water is greater than or equal to 75. If that's the case, what I'd like you to do is by looking at our LEDs, I simply want you to turn the green LED on and have the yellow and red be off, keeping in mind that you are going to have to index their LED pins because you have them stored in an array. Now that should be the easy part and something we've done in previous lessons. What I also want you to do is give our viewer a visual output of what the actual percentage is by using the LCD. To do this, we first have to set the cursor of the LCD to make its print where we want it to, and we want it to be under that original plant condition string that we wrote in the void setup. To do so, we are going to set the cursor to 0, 1. Now what that means is to the first column, second row, keeping in mind that our counting convention is such that we begin counting from 0. So 0 is actually the first column, and 1 is actually the second row. Once there, we're going to call LCD print and print the value of percent watered, and follow it with a string. Now that string is going to indicate the units we're using, which in this case are percent, and in the condition in which our percent watered is above 75, we are going to print the value good to the LCD to indicate to our farmer that plants are well watered. Now, 80 is a subtle little thing that we are doing, but that extra print of a completely blank space is known as a buffer. If you've never worked with LCDs before, here's a little known quirk. Once a value is printed to one of its spaces, it will remain there until overwritten, the program has been restarted, or the LCD has been disconnected from power. So in the event we have a percent, let's say that is 100, and we then dip down to double-digit percentages, we're going to have an open area where there's a 0 left over that we want to overwrite with a blank space so it doesn't remain on the screen. Now on line 84, you're going to see else if, which means unless I see this set of parameters being met, and in this case it's the percent watered being greater than or equal to 50%. Now I haven't given you any code inside of those curly braces, but I want you to mirror what we've just done in the original if statement, and I essentially want you at this case to turn the yellow LED on and the others off, and I want you to make an LCD print with the percentage, as well as the string indicating to the farmer that it is a fair condition. In our else statement, which essentially is saying, given any other situation besides the two we've already stated, so if you really think about it, it's anything less than 50%, what we want to do inside of these curly braces is turn on the red LED, we want to turn the green and yellows off, and in our string, we want to print the condition to be poor in addition to printing the percentage watered. And we're going to end our entire code with a slight delay because it does improve the simulation performance here in Tinkercad. If all goes well, your wiring is appropriate, and your code is correct, This is how your functioning circuit should operate. So first, let's remember something. The potentiometer is nothing more than our analog input, just like our moisture sensor. And keep in mind the behavior of the moisture sensor. As the readings go up, that indicates a drier condition. As the readings go down, that indicates a more watered condition. So, let's begin our simulation. And what we see here is that as the potentiometer is set to 0, that would indicate a completely watered condition. Now in real life, your moisture sensor is never really going to read 0. So we don't quite know exactly what watered is going to be until we test it in the lab. So let's assume we've put our moisture sensor into our pot, we've added the water that we think is appropriate, and the corresponding value of the moisture sensor is something in this range here. So now what we have to do is we have to reset the conditions of our watered variable by pushing our set button. And when we do that, you'll see that it reestablishes this new condition as a fully watered plant, and it lights the green LED. Now from here, if we continue to increase our sensor value, you're going to notice that we enter the fair range as we cross the 75% threshold, and our yellow LED is lit. And as we continue on past our 50% threshold, we get the poor condition on the LCD, and the red LED becomes lit. So we've proven here that we can create a simple monitoring system out of nothing more than a potentiometer, a button, a few LEDs, and an LCD screen to get some numerical output. Pretty good, guys. Very nice job.